In the previous video, we analyzed the non-inverting amplifier and we found that the output is related to the input using this relation. V output equals Rs plus Rf over Rs multiplied by the input source that is connected to the non-inverting input of the op-amp, which also can be written as V output equals 1 plus Rf over Rs multiplied by the source. Whatever you call the source, you call it Vs, you call it Vg, it doesn't matter. Where the source here is connected directly to the non-inverting input of the op-amp, which means that because there is no current here, Vp equals Vg, and also Vn equals to Vp equals to Vg. So here in the circuit that we analyzed, Vn, which is the voltage of the inverting input, equals to Vp equals to Vg, because there is no current here. Today we are going to solve an example on this non-inverting amplifier. So the example says that assume we have this circuit and assume ideal op-amp, find the output voltage when the variable resistor is set to 60 kilo ohm. And then it asks you how large can Rx be before the amplifier saturates. And of course the DC voltages are given as 5 and minus 5. So let's start with the first part of the question. If Rx is set to 60 kilo ohm, what will be the output of the op-amp? So the first thing to do is notice that the current here, the current in IP in the non-inverting input of the op-amp is 0. The current here is 0, which means that the current in the 15 kilo ohm will be the same exactly as the current in Rx. So the current in the 15 kilo ohm is the same as in the current in the Rx, which means that we can apply the voltage divider rule here in order to calculate the voltage across Rx. We can say that the voltage across Rx, which we can call the voltage across Rx is the same as Vp, right? So Vp equals to 400 millivolt multiplied by this resistor divided over the sum. So 400 millivolt multiplied by Rx over Rx plus 15 kilo. So let's keep all the resistors in kilo and the voltage we'll use it with the millivolt. So here Rx is given as 60 kilo ohm, so we can say that Vp will be 400 multiplied by 60 kilo over 60 kilo plus 15 kilo. You have to make all the units the same, right? So this is 60 over 75, which can be written as 400 multiplied by, if we divide over 15, it will be multiplied by 4 over 5, which will give you that Vp will be 320 millivolt. This is Vp, this is the voltage at the Rx, which is the same as the voltage in the non-inverting input. Type. For the op-amp, for the ideal op-amp, Vp equals to Vn. If we assume linear operation, Vp will be equal to Vn. So the voltage here, Vp is the same as Vn, assuming linear region, right? And this voltage is actually the voltage that was amplified in the non-inverting amplifier that we analyzed in the previous slide. So if we look at that non-inverting amplifier that we analyzed in the previous slide, Vp was equal to Vg, and this is the voltage that was amplified using this relation, right? So you can directly use this relation for the non-inverting amplifier, and you say that in this case the output will be equal to Vp multiplied by 1 plus Rf over Rs, and this will be 320 millivolt multiplied by 1 plus Rf is the feedback resistor, 63 kilo divided by Rs, which is 4.5 kilo, so 63 over 4.5 which will give you, this is 63 over 4.5, this is like, if we multiply both the numerator and denominator by 2, it will be 126 over 9, which will give you probably around 14. Okay, 14 plus 1 is 15, so this will be 320 multiplied by 15. Okay, which will be 320 multiplied by 15. You can calculate the voltage here. We can do it quickly. So this will be 3,005 times 5 times 160. So this will give 4,800 millivolt. 4,800 millivolt is within the range between -5 and 5. So we say here that our assumption is correct. Why? Because 4,800 is lies between -5 and 5. So the assumption is correct and the solution is also correct. The next step, it says how large Rx can be before the op-amp saturates. Of course, as Rx increases, the voltage here increases and the output voltage will increase, right? So if the voltage across Rx increases, Vp increases, Vn increases, and hence V out increases until it reaches 5 volt, and then V output will saturate. So the question here is how large Rx can be. So what we'll do is we'll calculate the output in terms of Rx. So we'll say that Vp in general, for a general Rx, Vp was equal to 400 Rx divided over Rx plus 15K, right? Then V output equals Vp, V output equals Vp, which is the same as Vn, multiplied by 63, 1 plus 63 over 4.5, which we calculated to be 15. So V out equals 15 Vp. So V out equals 15 multiplied by 400 Rx over Rx plus 15. Okay? And this is the equation for V output in terms of Rx. So in order for the op-amp not to saturate, we need V output to be less than 5 volt. But take care that we used here 400 millivolts. So the units of the volt here were millivolt. So we need to change it to volt, or we change the 5 to millivolt. So we can say now that 15 multiplied by 0.4 volt multiplied by Rx over Rx plus 15 must be less than or equal to 5. Now this is in volt, this is in volt, right? And all the resistors are in kilo ohm. Okay? So now what we should do is we should do some mathematical manipulation. We can say that now Rx over Rx plus 15 must be less than or equal to 1 over 1.2, and then crisscross will get that 1.2 Rx must be less than or equal to Rx plus 15, which means that Rx must be less than or equal to 15 over 0.2, which is 75 kilo ohm. So Rx must be less than 70 or equal 75 kilo ohm. This is the maximum Rx that allows this circuit to operate without any saturation. Okay, we'll stop this video here and see you in the next video.